Okay, so the first thing I wanted to point out was that the reading has moved on. So now we have chapter 10 in Wunsch, which is about the large-scale ocean circulation, and it will have a lot of the same theories we're talking about in a very calm and orderly way, with the slightly different notation on the equations. But I'm hoping that just like from the homework, in reconciling the notation we're using in class and the notation that Wunsch is using, you're actually learning, thinking it through in terms of units and vectors and directions and all of that, because they're easy to screw up. And then calling chapter 4 has just a lot of really beautiful schematics, and not so much on the equations, not so much on the words are okay, but the schematics are really, really nice. So you can go through those and think about the way that the different forces we're talking about in a kind of from a different perspective. I'm showing a lot of the schematics in the slides, but there are more to look at in the chapter than we're going through as well. All right, so first I'll have questions, if you guys have questions, but then we're going to go through our review of balances again, and now we have a new one from last time, the thermal wind balance that we got to at the end. And then we're going to talk about geostrophic flows that result from Ekman convergence and divergence. There are going to be two flavors of that. One is the gyres that we've been kind of hinting at, but also the eastern boundary upwelling systems, which a lot of you are writing your papers on eastern boundary upwelling systems. And I could tell from the plans that there was some confusion about what's going on. So I want to go back to those schematics. We've actually seen the schematics already, but walk it through a little more carefully, thinking about which direction the Ekman transport goes, which direction where that leaves the low pressure, where the high pressure would be, what kind of geostrophic circulation that would imply, and so on and so forth. So we're going to go through that part first before we go to the gyre. And then, as time permits, we're going to touch on the shallow water equations, which is almost too much of a topic for this class because we don't use them directly, but they simplify things when we get to the waves a little bit. It's a different way of thinking about the equations of motion, but it allows us to think a little bit about like how a model works and how you might think about different kind of models. So I think we should touch on it a little, but I don't expect hardly any of you to have to follow the details on this, but I wanted to give you a little taste of what it's like because it will help later. And there's one key concept that we'll bring up that will be helpful. All right. So, questions? Are there any? Yeah.
On the document that you gave us, in it, there's kind of like a step-by-step procedure for the budget.
Yeah.
And in one of the sections, it only talked about like doing the advective fluxes. Should we also use the DF fluxes?
You can add those together, and they have sort of obvious naming. The diffusive fluxes are like kind of hard to interpret because there are a lot of weird, crazy things that get kind of stuffed into that term. Frequently, they just won't matter very much. And so the simple thing to do is the advective ones will make sense to you. The advective ones will be the things we're talking about in class. Upwelling will be represented in advection, and it will look like the vertical velocity field. So you'll be able to interpret that one. The reason why I de-emphasize the diffusive part is because it's things like subgrid scale, mixing, and complicated other things that we don't really have time to touch on. So you can add them in and just say that's the kind of thing that's in there, but I wouldn't expect anybody to dig into the details of what those mean. So that, take that as you will. The easiest thing to do is to check and see if it matters much. If it doesn't matter much, then you can either add it or not add it, your choice, and it won't really affect the answer.
Okay.
Yeah, in general, that's actually the best thing to do when you have something that you don't want to deal with, right, is to check whether it matters, and if it doesn't matter, then your options are open. But so it's a little bit like the nonlinear term and the momentum equation. We don't want to deal with it, but one of the advantages of this whole approach that we're building is you can easily consider it or not consider it by contrasting what you see versus what's in the model, because that's kind of the big difference that's there. So, but the diffusive terms are a similar complicated thing that we're not talking about in detail, which might be regionally important, and the model doesn't work without them, but it's not something that we need to dwell on.
Okay.
Other questions? All right. Okay, so this is the momentum equation, which we have been staring at a lot. All right, so these are inertial oscillations. Which one is an inertial oscillation? When did we see these? The wobbling of the curtains in the tank. And then we talked a little bit on the Coriolis day about the ellipses as you go around the Earth, overshooting on one end and overshooting on the other, if you were making the little inertial oscillation circles. And we saw some of the drifters that were also doing those inertial loop-de-loops. So these are ubiquitous throughout the ocean. Frequently they have a lot of energy in them, much more energy than the tides or other things, but they kind of don't do a lot except for swash around in circles. So, but it's important, and it's our only large or order 1 Rossby number balance that we think about. So that's another reason why it's useful to think about. And we have the Ekman layer. So what forces get balanced in the Ekman layer?
Wind and
Coriolis and wind, or Coriolis and friction. So in the Ekman spiral, you're dragging both on above and below, and so you spiral around to the right. In the Ekman transport, it's the layer integrated force balance, and then it's wind versus Coriolis that are the only balances. Hydrostatic balance. So what's different about this one? The direction? Yeah, this is the one that's in the vertical. So, and this is pretty much the only one that we worry about in the vertical. So the others are all horizontal momentum balances. This is a vertical momentum balance. Here's the geostrophic balance. So how does this one work? Yeah. So the pressure gradient is in balance with the Coriolis force, the same way as the friction was in balance with the Coriolis force in the Ekman balance. And where does the pressure come from?
Changes in the sea surface height.
Changes in the sea surface height, changes in the density through the hydrostatic balance. The Taylor-Proudman theorem is kind of a combination of the geostrophic balance and the hydrostatic balance in the particular case of barotropic or constant density flows. And this one is kind of elaborate. We didn't come to it in an elaborate way, but it's a useful way of thinking about how rotating fluids work, right? So what's the characteristic kind of motion? Curtains or columns of motion. So they don't tip over, they stay straight. So it's kind of two-dimensional as it's zooming around. Okay, so here's the new one, thermal wind balance. So the thermal wind, which is sort of the deviation away from Taylor-Proudman, is you put together the geostrophic part and the hydrostatic part using the buoyancy, which makes it a little easier to think about, then the gradient, or the vertical derivative of the geostrophic velocity in the direction of the rotation axis, dz, is affected by the gradient and buoyancy. So now this is a tilting. This is something away from the Taylor-Proudman theorem. It's a tilting over with height, because the velocity is different at different levels, different high, low, depending on horizontal variations in buoyancy. So horizontal variations in buoyancy are essentially baroclinic stuff. It's where the fluid is anomalously light or anomalously heavy compared to the pressure field that it's in. Okay? And we use buoyancy, one, because it's easier to think about the density for this reason, but it's also just makes this equation really clean because it drops g's and other things that appear if you just combine those two. Okay? All right, so we showed this movie on the first day. So what do you see now that you have a better sense of what's going on? So this movie is showing sea surface temperature, and obviously the motion is largely because of currents. And the clock is in months, which is useful for time scales. So what's happening with temperature on the currents that are flowing?
There are little gyres of temperature in the flow. It's not perfectly straight.
Yeah, so it's not laminar. That is, it's swirly. And so those turbulent features on this scale are called eddies. And we're going to talk a lot more about eddies. But also, is the temperature constant on the currents? Or is the temperature a gradient on the currents? Like, does it vary across the current? And what does that have to do with the thermal wind? Now we go to the equator, but none of the stuff we talked about applies. But anyway, this is cool. That's a big El Nino. And then, zing, now it turns into La Nina. But see what I'm saying? Like, look at these tropical instability waves. You can see that they're hot on one side and cooler on the other side. So what does that mean about the buoyancy across the front?
Temperature affects the density, so then you have a pressure gradient I assume in the direction of the flow.
No, it's in the direction across the flow because these are largely geostrophic flows. They're big, but yes, that's exactly the right idea. Is that it's light water on one side, dense water on the other side. Their pressure gradient set up by that. There would be a cross-flow pressure gradient in balance with the Coriolis force, so making it a long flow direction. And then because these currents are typically surface intensified and they decrease with depth, there's also a thermal wind part involved. And so that temperature gradient across the sides of the current has everything to do with the thermal wind part. Remember, it's the horizontal buoyancy difference. It's the horizontal buoyancy difference across, there's a cross product here, so it's across the flow direction, across the shear direction, that the density gradients are important. And I showed this movie for reasons I don't remember. But anyway, okay. So last time when we were talking about geostrophy, we started thinking about high pressure cells, low pressure systems. So what happens when you have a high pressure system? Which way does the flow want to go? It wants to go anticyclonic because the pressure gradient force pushes which way? Outward. So that's the pressure gradient force, which means we want a Coriolis force to oppose it. So the Coriolis force is inward. So how do I get a Coriolis force inward? I have to go this way, around the circle. So that way, which is clockwise. This is northern hemisphere. When did I make the assumption that it was northern hemisphere? The Coriolis force is to the right of the motion. If I had done the same thing, I still would have said the pressure gradient force pushed outward. The Coriolis force had to push inward, but I would have said in order to get a Coriolis force to push inward, I needed the flow to go the other way in the southern hemisphere. So this is which? Cyclonic or anticyclonic? Anticyclonic. And so the anticyclonic in the northern hemisphere is clockwise, anticyclonic in the southern hemisphere is counterclockwise. And cyclonic is a low pressure system, and it goes the other way around, both hemispheres. Okay. So our explanation for gyres that we started thinking about, we had these pressure cells that were set up where there's high pressure here, here, low pressure here. And so the high pressure in the center of the subtropical gyres, so the subtropical gyres are the ones that are not in the tropics, and they're subtropics. So they're slightly before you get to the tropics is the way that it goes. And then subpolar gyres, or the Antarctic circumpolar current, are not at the poles. They're slightly before you get to the poles. So that's a simple way to remember it. The subtropical gyres tended to have Ekman convergences, which will tend to lead to a high pressure anomaly, and then a high pressure anomaly leads to cyclonic flow. So which way does this gyre flow? This high pressure subtropical gyre in the Pacific? Clockwise. So the Curcio as it comes off is part of that, and then it loops around like this. And the same is true of the Gulf Stream and the Atlantic subtropical gyre. But on the other side, the East Australia current goes this way. And it's still a high pressure, but it's just in the other hemisphere. So it's an anticyclone. The subtropical gyres are all anticyclones, but they go different ways in different hemispheres because of the Coriolis force flipping side. Okay? And so one of the questions, though, that you might say, so this is a map of kinetic energy. So we can't even see the return path of these subtropical gyres. What does that mean about the rate of flow? It's slower, has lower energy. We know that it goes around. How do we know that it goes around? Conservation of mass, approximately, right? We know that the water doesn't just disappear, so it's got to come out some way, and we've actually seen in other figures that it should loop around. But it's coming back much slower through here. So one of the things, and one of the next pieces that we want to start thinking about, which is noticed by a guy named Henry Stommel, who worked at Woods Hole, is that all of these gyres, regardless of which hemisphere they're in, or whether they're subtropical or subpolar, tend to have really strong currents on their western side compared to the eastern. So big current on the west, 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 big current on the west. So there's something else going on that we haven't got the tools yet to explain why west is different from east. And it's particularly confusing because it doesn't switch from like west to east in the northern and southern hemispheres. It's always in the west, regardless of which hemisphere it is. So it's a peculiar one. Yeah?
Could you describe it in terms of the difference between the equator and the poles? Would there be a variance in that?
It is very closely related to that. So it's essentially, the key factor we'll see is because the Coriolis parameter is changing with latitude, to become more and more like the North Pole the more north you go. So F starts off at a negative number at the South Pole and it becomes a positive number. So its derivative as a function of latitude is always of the same sign. And we'll see that its derivative is a key part of this whole story. Okay, so we're building towards that. And all these currents have fancy names. And there's all kinds of interesting little wiggles in different parts of the world that have to do with topography or local pieces. But this basic pattern of having gyres that spin in the anticyclonic direction in the subtropics, and then other gyres spinning in the cyclonic direction in the subpolar regions, is consistent. And the ACC is kind of one huge, it's not quite a gyre, but it is a low pressure system, and it goes around and around and around the pole. Okay. So let's start to think about what sets up these pressures. And then let's think about how they work. So we can think about Ekman convergence to divergence. We've got all the tools to think about that. We might wonder about why it's stronger on the west. That's going to take us a while to get to, but we'll start thinking about it today. What about the eastern boundary currents? On the other side, all the upwelling zones we're doing for the paper. Are there deep boundary currents? Like what's going? We've been looking at surface currents, but something else magical happening down deep. And then we'll talk a little bit about that, but not too much. Okay, so remember this is our chlorophyll and SST, and we can see all these upwelling zones, both the coastal upwelling zones and the equatorial upwelling zones. And then also the broad scale upwelling throughout the Southern Ocean and the subpolar gyre up there. Southern Ocean. So we know that the wind stress curl here is upwelling favorable throughout the whole subpolar regions. And then the wind stresses here are along shore in such a sense as to drive the surface waters off. And then they are easterly along the equator in such a sense as to drive the waters to the north in the northern hemisphere, to the south in the southern hemisphere. And then the SSTs, which are not as obvious as the chlorophyll, have similar low SSTs where the chlorophyll is high, because this is bringing up deep water, which is both nutrient rich and cooler. Yeah?
Why is there like gray area other than the cloud in the left-hand side?
Oh, these little blobs? Sorry, those are clouds. This instrument can't see through clouds. So this is actually, these are real observations from a satellite. And so this instrument, whenever there's a cloud there, they just don't have any data. On this side, this is actually a sensor that can see through clouds because it uses a different part of the electromagnetic spectrum that penetrates through clouds. So they don't have the problem with clouds in the temperature record. Okay. So let's remind ourselves how the Ekman pieces work. So here's the equatorial piece. So the winds come from the east to the west, and then what happens? So the Coriolis force needs to be in that direction. But why is the Ekman transport away?
There's a divergence in F, or
Yeah.
a different sign on each side.
You can think of the divergence in F having different signs. So the curl of tau over F, which we know is the Ekman divergence, flips. That's true. Or you could just think more simply, in the northern hemisphere, you tend to flow to the right of the wind. In the southern hemisphere, you tend to flow to the left of the wind. So if the winds span the equator, the right-hand side is going to the right, the left-hand side is going to the left, and you get a divergence. Those are equivalent explanations. Okay? And so along the equator, we might see something like this, where this colder water is being brought up, there's mixing going on, the surface has a residual of the flow away, a little bit of low pressure there, and then the picnic line is being brought up. When the surface comes down and the picnic line comes up, what's the pressure gradient like down here?
Constant.
Closer to constant, yeah. So a picnic line elevation under a sea surface depression is like having a short stack of pillows and then a little bit of bricks at the bottom. And so you end up not having as much of a pressure gradient below. And so this is what we expect to see when the flow is concentrated at the surface rather than penetrating down. Okay. So at the equator, we can't use the geostrophic balance. Why not? Because there's no Coriolis force. So F is 0. So if we write F cross V equals minus grad P over rho naught, that's 0. So we have trouble understanding that balance. But away from the equator, we might expect there still to be similar kinds of sea surface height minima from a divergence reason, picnic line being pulled up, and then let's think about the geostrophic currents that result. So that's this case. We have an alongshore wind along a coastal region, and this is in the northern hemisphere. The Ekman transport is going to go offshore. So this is key for your paper. When you diagnose the Ekman transport from the alongshore wind, it's not going to be in the direction of the alongshore current. So if you're in the Peru current, if you're in the Canary current, if you're in the California current, the current itself is not the Ekman transport. The offshore flow is the Ekman transport. But what's that offshore flow going to do to the pressure over here? It's going to make a low, just kind of like it did here. If there's low pressure here and relatively higher pressure here, which way does the geostrophic flow go? So, not something this way. We did this one, or we did the other one. Vg equals z hat cross grad p over rho naught m. So, okay, so which way is the pressure gradient if this is low and this is high? From low to high. So the pressure gradient force is that way, the other way. That's this. So F crossed into what direction? F is vertical. What direction of flow will point in the same direction as the pressure gradient force? F, this way, points down. So the eastern boundary current is going in such a way that the Coriolis force on it is opposing the pressure gradient, the Coriolis force on it to its right is opposing the pressure gradient force, and so it's in balance going this way. Everybody following me? So the eastern boundary current is actually a geostrophic current that is there because of the Ekman transport setting up a pressure field. Okay, so there's two layers. First, we get the offshore flow from the Ekman transport. The offshore flow sets up a pressure field, and then the pressure field has a geostrophic flow associated with it. So for this paper, we're not really going to diagnose the geostrophic balance, but you might want to look at the variable called phi hyd, which is the hydrostatic pressure field. It's actually pressure over density, so it's not the same units as pressure, but it points in the same direction. The flow of those currents should be roughly along that pressure field. So if you made a map of it, you would see that it was have contours, isobars, at a given depth, showing you where the current's flowing, essentially. Okay? All right, so, but here's the picnic line getting pulled up by this. Why is the picnic line getting pulled up? The lower surface to reduce the pressure gradients down here. In some of these boundary currents, it doesn't perfectly cancel, and in fact, you get a reversal of another undercurrent flowing the opposite direction. So these two are kind of drawn as being on top of each other. So is this one consistent with the Taylor-Proudman idea of how things work? Not at all, because it flows at different directions at different depths. So if it is not Taylor-Proudman, then what must be at play? Thermal wind, baroclinic effects. So we expect to see buoyancy gradients. And hey, look, here's a buoyancy gradient. That's cold water sitting right next to warm water. Or dense, deeper water sitting right next to warmer water. So the vertical shear has everything to do with that temperature gradient that's being pulled up by the upwelling. So the upwelling is making a temperature gradient, the upwelling is making a pressure gradient, a pressure field. The pressure field has a surface boundary current, has a deep boundary current. The difference between those two has to do with the lateral differences in temperature, or the lateral differences in buoyancy. Okay? So all these pieces are linking back together. Okay, so a lot of you are interested in the seasonal variability of this kind of current. If I turn off the winds, what happens? It stops. What stops?
Well, the Ekman transport would stop, so then that would stop creating the upwelling over there.
Yeah.
And then because of that, the pressure gradient and the temperature gradient wouldn't be set up, so then the current would move.
Right. So, interestingly, it doesn't stop quite as simply as you might think. It isn't like it just shuts down, shuts down, shuts down. You turn off the wind and then it starts having inertial oscillations. And these things start bouncing around and waves propagate away, and it's all very complicated on the time scale of a few days to maybe a week. But season to season, as the wind goes up and down, you can neglect all of those quick transient things, and you essentially would just say the Ekman transport is going up and down, and along with it, the strength of the upwelling is going up and down, and along with it, the strength of the pressure field is going up and down, and along with it, the strength of the boundary current is going up and down. So they should all link together on a kind of month-by-month time scale. On a shorter time scale, there would be more wobbles, but on a longer time scale, maybe not so much. So it's not crazy to look at the strength of the boundary current and how it relates to wind stress for that reason. Even though the boundary current is not directly caused by the wind stress, it's caused by this chain of events. The winds make the upwelling makes the pressures and buoyancy, and the buoyancies and the pressures make the currents. Okay? Okay, so here are some of the schematics from the Calling book, which are these are showing different varieties of upwelling zones, which you might find that have to do with like exactly how the upwelling strength fits versus the local topography. So there's the continental shelf and the continental slope, and the continental shelf might be shallow, and then there's a continental slope that's deeper. The continental shelf might be kind of steep, and the continental slope goes like this. ECHO is a relatively coarse resolution model, so in most of the world, the continental shelf is not very well resolved. Maybe off the east coast of the US where you have a really, really wide continental shelf, you might see a lot of that. But typically this might only be one grid cell, kind of or a couple grid cells in the shallow part before it drops off. So you won't be able to see a whole lot of structure there, but you can easily imagine the picnic line coming up and meeting kind of right at the edge, the picnic line coming up and meeting the surface there and having some kind of closed shelf circulation. The picnic line coming up offshore a little bit, but there's still a deep water circulation that comes up and makes a cold surfacing before it comes back. Does that make sense to everybody? And it's kind of the wind strength versus the local topography is what would govern this. But now look at these little ins and outs of the board. What are those supposed to symbolize? boundary currents of different kinds. So this one has a current coming towards you at the top and going into the board at the bottom. So it has both an equatorial, it has both an eastern boundary current and a deeper undercurrent in the opposite direction. This one has an eastern boundary current and then an undercurrent off the slope, but then an eastern boundary current with no undercurrent on the shelf. And that's because, look, it's relatively uniform in temperature over here, so there's no buoyancy gradient to have a thermal wind shear. So if it's relatively uniform temperature, relatively uniform buoyancy, then you wouldn't have that kind of, you might not have that return undercurrent underneath. And then down here, it's even more complicated because there's kind of a side-by-side equatorial current, eastern boundary current and undercurrent, but they're kind of side-by-side from each other because of the shape of the picnic line. Okay? And all of these are just applications of geostrophy, these same two rules, and with these different temperature or buoyancy layouts. Okay? Okay, so let's remind ourselves of the thermal wind one more time. So if we have light water next to dense water, buoyancy gradient goes which way? From the low buoyancy, the dense stuff, to the high buoyancy, the light stuff. So these green arrows showing us that. So we could immediately go to dV/dz from gradient of buoyancy, negative gradient of buoyancy if we wanted. Or this is the one that inverts that, so dV/dz equals z hat cross the gradient of buoyancy. So z hat crossed into the gradient of buoyancy is positive that way. So out of the board at the top, into the board at the bottom. That's this equation. But we can also think about it in terms of pressures. So there's higher pressure here and lower pressure there. Why is that? Yeah, because when we have light stuff next to dense stuff, we're typically expecting there to be a sea surface high next to the light stuff. If that wasn't the case, that wouldn't be the normal situation, but that's the typical situation. And then at the bottom, we have lower pressure here and higher pressure there. Why is that?
We're deep enough that the height differences don't matter as much.
Yeah, and also the hydrostatic balance is the weight of the stuff above you. So a lot of bricks weighs a lot more than a lot of pillows, even if you started counting a little bit earlier. So the pressure gradient is now reverse direction at depth. So this is the pressure gradient force at the top, this is the pressure gradient force at the bottom. So look, the geostrophic flow that goes with this pressure gradient force is in, geostrophic force that goes with this pressure gradient force is out. So all that the thermal wind is the combination of hydrostatic, so vertical pressure distribution, high, low, high, and geostrophic. Pressure gradient in the horizontal from high to low this way, out, high to low, in. Okay? So it's the combination of the two ideas to get. Any questions on this? Everybody seems very puzzled by this. Okay. All right. So now let's think. We thought about the eastern boundary current side, and in that case, we had essentially a divergence of the Ekman transport because one side was the wall, and one side was the offshore flow, and that divergence drove upwelling, and that upwelling brought up cold water, and then kicked off the low pressures and all that stuff. Let's think on a global scale instead. So this is the approximate direction of the climatological wind, so the mean wind direction. And here are equatorial winds, which are going from the east to the west. Here are the roaring 40s going from the west to the east, from the west to the east. Okay, westerlies, easterlies, westerlies. So we put simple arrows on them to remind us. Okay, so which way is the Ekman transport going to go on because of this one? South. What about this one? North. What about this one? Both. So what's happening in between this arrow and this arrow? Convergence. What's happening on this side of this arrow? Divergence. So away from, nothing up here, small winds, to a wind that's driving a southward flow. So little arrows like this. So Ekman transports. Everybody with me? So convergence, divergence, convergence, convergence, divergence, 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 convergence, 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 divergence. Okay. Convergence is what makes what? A high pressure or low pressure? A high. So cyclone or anticyclone? Anticyclone. Highs have anticyclones. Lows have cyclones. And this enormous low has a huge cyclone that goes all the way around the planet and comes back. Okay? This is essentially the structure of the oceanic currents. So let's look at what those look like. Here's the pressure field, and here's the velocity field. So how do I read the flow on the pressure contours? Which way does the flow go relative to the contours? Along the pressure contours. The pressure gradient is perpendicular to the contours. So the geostrophic flow, which is perpendicular to the pressure gradient, is along the contours. Okay? So here's the Kuroshio, and then here's the return flow for the Kuroshio. Here's the Gulf Stream, and the return flow for the Gulf Stream. And here is the same thing, just in kinetic energy. So you can see that clustered set of pressure fields has a lot of kinetic energy. This clustered set has a lot of kinetic energy. This spread out set doesn't have a lot of kinetic energy. Why is that? Using this equation. Yeah. So the closer the pressure contours are, that is, the faster the rise in pressure for the run and distance, the bigger the pressure gradient is. And the geostrophic relationship tells us when the pressure gradient is big, so is the velocity. So the velocity is big here because the pressure contours are close together. Pressure contours are close together, the pressure gradient is big, the geostrophic velocity is big. Over here, the pressure gradient is there, but it's small, so the return flow is coming back along those, but it's not coming back very fast. So it doesn't really appear here in the kinetic energy, even though it's there. It's just about 100 times smaller, or in kinetic energy, about 10,000 times smaller. The velocity is about 100 times smaller. The kinetic energy is about that squared. Okay? Oh, I should have said this is a log scale for energy instead of, it's log 10. But anyway, that's still fine. Okay, what about down here in the ACC? How's that one working? Which side has low pressure? The pole, the southern side. And then, which way is the flow? Along these pressure contours this way. And where are some of the more intense regions of the flow? It's kind of slowing down and speeding up as those contours converge and diverge. Where's an intense region? This is also a test of your southern hemisphere geography.
South Georgia.
Near South Georgia. Okay, there we go. Oh, here we go. And so, yeah, so there's kind of out here, they're a bunch. Over here, they're a bunch. Here, they're a bunch. So there are these regions where you're getting piles up, where the current is accelerating or concentrating itself, which has to do with both topography and the winds and a lot of other features that guide this, but those accelerated places are actually relatively stable for where they are. But there are lots and lots of eddies superimposed on this as well. I had another question which I was going to ask. Oh, one way to remember which way the geostrophic current goes. Okay, this has high pressure next to low pressure. So if it wasn't for the Coriolis force, which way would the high pressure go? South, right? The Coriolis force turns it which direction? To the left, in the southern, to the left of that flow in the southern hemisphere. So if you just imagine the light water running down, or the high pressure water running, and then bend it with the Coriolis force, you actually get the right direction. So you can go through from the equation, but then you forget whether or not there's a minus sign. You can go through from the Coriolis this way, pressure gradient force that way, get a balance, and then do it. But you could also make mistakes with the cross product, or use your left hand instead of your right hand on the right hand rule, which is easy to do. I'm trying to give you a lot of mnemonics to have consistency in the way that you think of it. Similarly, this high pressure water would want to flow out, but it gets bent which direction when it's doing that in the northern hemisphere? To the right of its motion. So this way, so if it goes out this way, it would turn and go right. That's correct. If it goes out this way, it would turn and go right. If it goes out this way, it would turn and go right. So it works the whole way around. So it works in both hemispheres if you're thinking of the light water kind of trying, or the high pressure water trying to escape. That's a useful way to do it. It also works with the thermal wind. Oops. Come on. If you think about the light stuff wanting to run that way and then getting bent this way, then it actually is going the right stuff. But on the bottom, you think of the dense stuff wanting to run this way and getting bent in, it works. So you want to go from the high pressure to the low pressure to have it make sense. Does that make? And that'll help you figure out which way things are supposed to go. Okay. All right. So we've already seen this picture of the gyre from the side. So this is basically just a 3D picture that we have sea surface height, and we have the pictocline depressed underneath. If this was constant density, we actually could figure out the pressure field from just the sea surface height. Because we know how to do that. We just integrate down. And so we go, the pressure equals the weight above you per unit area, and you go through a bunch of calculations, converting the density, the horizontal gradient, to the horizontal gradient of sea surface height, with the right factors out front, follow on, and you come to this equation. So here is this is the geostrophic relationship at the surface, assuming that all of the density is constant, just in that surface layer. So this tells us what? This says high pressures, the thing that are getting anticyclonically spiraled around, are because of sea surface height highs. Low pressures, so you can compare to this if you want. Low pressures are sea surface height lows. And you get an F cross velocity spiraling around it in the same way as we have before. Okay? I don't know why I repeated that slide. Oh, here we go. Like this. Here we go. So if this is our balance, we can just write this out component by component. So here's the eastward velocity, which has to do with the sea surface height gradient in the north-south direction. And here is the southward, the northward velocity, or southward with the minus sign, which has to do with the east-west gradient in sea surface height. Okay. So here is high, here is low. So d eta dx is what sign? And x is increasing in that direction. And goes down. So d eta dx is negative. Because it goes from high to low as x increases. Okay? So this is negative. So this side, whole thing is positive. So this is negative. So the flow here is southward. That's the right direction for the northern hemisphere of gyre. What about from here to here? What's the direct derivative of d eta dx? Positive, because now it's going from a low value to a high value as x increases. So this is northward flow. And you do the same thing on that side and the same thing on that side with this equation. Okay? Or we could be even fancier and we could integrate the geostrophic velocity in the x direction from some eastern boundary value to some intermediate value, some western side of whatever our integral is going. And then we find that it's going to be just, so if I integrate this in x, since it's a perfect derivative with x, it just becomes the value of eta at the boundaries. So the x integrated flow, the net flow between this point and this point southward, is just proportional to the difference in sea surface heights between them. To put it another way, the sea surface height over f is the stream function of the geostrophic flow. So this is the way you write a stream function. So for those of you who've done fluid dynamics and know what a stream function is, this makes sense. For those of you who haven't, this doesn't make any sense. But anyway, this relationship, this is the way you find the stream function from a velocity field. And this is saying that this object, g over f times eta, is acting as the stream function. So g over f times eta is actually the thing that, if you contour it, the flow will flow along those contours. Okay? In this constant density case. And we could also integrate from top to bottom. And now we have the mass transport coming through that phase. If I integrate from top to bottom. And then that's g times h over f times eta. Oh, wow. Something I hadn't realized before. It's in that. But anyway. We don't need to dwell on it. It's a little. So the mass transport between, say, this point, which if that point's the top, and this point is the bottom, the mass transport southward is just the difference in height from here to there. Okay, here's the quiz question. How high is it here compared to there? It's the same. Why is it the same?
Well, if we take the cross section through the gyre, everything's circulating, so the net transport should be 0. So the difference in eta should be 0 too.
So based on this, if I take from this side over, I get the net southward transport, and that's this eta minus this eta. If I go this way, it's this eta minus this eta, and they have to be in opposite directions, so it goes down as much across this return flow as it went up on the other side. Okay? So this is a really powerful idea. Now it doesn't matter whether this lump is in the middle or way over here on the side. What happens if the lump was way over here on the side? It would still have to be eta is the same. It would still have to be the net flow on this side equals the net flow on that side. Which flow is going to be the fast side?
The one closer to the hump.
The one closer to the hump. So now now let's go back and look at our pressure field again. We have a pressure field where the high of the pressure is right here against the side. And then we have pressure contours going like that. So eta is, in fact, look, this contour is the same contour that's on that side, almost, roughly. There is a reason why that's not actually true, but we'll talk about that in a second. That one equals that one. So as we count up the pressure contours, we're actually counting the volume flow going that way. As we count down the pressure contours on that side, it's the volume flow going that way. That makes sense to everybody? And so all the velocities are piled up on the western side because the center of the hill is all the way in the west. We still don't have an explanation for why that is, but we can at least see a consistency between the pressure field and the velocity field and the conservation of volume. Okay, what if I choose to add another current on top of that? What if I say there, it's like this, and that's the gyre, but on top of it, I've also got some other flow that just happens to be zooming by and goes right past the gyre and continues on out. So in the Atlantic, there is a flow that does that. It's heading north, and then it goes out into the Arctic. Now what can I say about the height here and the height there? Do they have to be equal? No, because the northward transport is a little bigger than the southward transport. So is it going to be shallower here or shallower, not shallower, whatever. Lower elevation here or lower elevation there? It's got to be lower on the left because we have extra flow. So we need x a to e to be even lower still to account for a little extra flow going through. A to E minus A to W on that side is not going to be as big. If I put some other upwelling driven current on this side, what would happen to eta at xe? I want to put a little bit of extra southward transport on this side. Is it going to make it shallower? Make it lower elevation or make it higher? Going to make it a little bit lower. So once again, we've seen that our upwelling driven current actually has a sea surface high low on the shoreward side of it. Okay? All right, starting to think about these pieces. So when I said that this was a stream function, that logic I just went through is what I meant. The stream function is the way of thinking about the integrated mass transport. And so if the stream function, when the stream function accumulates, it has to go back down, and the flow flows along, steady flow flows along the direction, along the lines of the stream function. Okay? So whether or not you knew what stream function was before, those kind of arguments I just went through helped guide the way you'd interpret a stream function. So this object right here, GH over F times eta, behaves as a stream function for the constant density ocean. So we've done all those? Okay. All right, now we're going to do one more crazy thing. Okay, here's our geostrophic flow, which we just talked about. So it's GH over F times eta. At the same time, we have Ekman, and if our wind was just westerly, that would be tau x over rho f. If I integrate it in the x direction, it would be xe minus xw. So everybody saw this one before. So this is what the Ekman depth integrated mass transport of Ekman, right? And then if I integrate and the wind was constant, I would just get xe minus xw. Okay? So now the cool thing is we can compare this formula to this formula and say how much volume transport in the north-south direction do I expect given a sea surface height field and a wind stress. And they both depend inversely on F, so it doesn't matter what F's doing. F doesn't get to play a role, and the densities are already being canceled out. This is just a background density point, so it's basically just the comparison of differences in sea surface height with a depth of how deep you go, how deep the motion goes before it stops, and then the wind stress. If I plug in typical numbers for this, I get about 10 sphere drops. Does everybody remember what a sphere drop is? We said this very briefly at the beginning. A sphere drop is 10 to the 6th cubic meters per second. So 1,000,000 cubic meters per second, or 1,000,000,000 cubic kilograms per second. So it is an awful lot. It's about the same as all of the rainfall on Earth. The Gulf Stream is 30 to 45 sphere drops. The ACC is about 140 sphere drops. So ocean currents are carrying an awful lot of water compared to evaporation and precipitation and rivers and all of that. That's part of the whole thing. But anyway, so this is saying for typical conditions, we might expect the wind across a basin to be pushing 10 sphere drops southward for westerlies. So that little purple arrow that we drew off of it moves about 10 sphere drops of water. For the same setup with the same typical difference in ETAs of 1 meter, we get about 100 sphere drops of transport. So this is a little funny because why are the ETAs here? Because of the Ekman. So this is a really weirdly efficient system. You move around 10 sphere drops of water, but the convergence of that ends up driving 10 times as much water around in a circle. That kind of amplification is actually typical of rotating fluids. That small accumulations, small ageostrophic effects, drive very large geostrophic responses because of subtle convergences and divergences are not allowed in the geostrophic part, but they are allowed in the Ekman part. So it's kind of a funny amplification system. So the gyres are there because of a much weaker Ekman transport. Okay? And we can come back to these kind of comparisons again. How does the little one drive the big one? And we're going to turn to something called vorticity next time to start to think about big ones driving little ones and a kind of useful way of thinking about how that works. All right, we've seen this. Oh, we haven't seen this. What happens down at the bottom? It might go the other way around if this dip was deep enough that it overcompensated. Or it might just exactly cancel out and there wouldn't be any flow at the bottom, et cetera, et cetera. There are lots of things to wonder about. In the 50s, Stommel and Aaron had a sense that there should be a flow pattern which looks kind of like gyres, but now notice there's no difference between subtropical and subpolar. And it's going like all the way down. And he was doing this on the basis of where deep water formation sites were. So if you cool water up here and it sinks to the bottom, where does it spread out? And this was a pattern that is sort of consistent. We're going to come back to this discussion later. This has a different explanation, but it draws in a lot of the same ideas of like western versus eastern asymmetry, pressure anomalies. We'd have to think our way through to get there. A slightly more modern conception, this is a beautiful paper from Susan Lozier from 2010, actually says that you shouldn't worry about the mean because what's really going on at the bottom is the eddies are so strong that most of the transport is just carried around by eddies. And this is still like not well understood what really is the right way to think about the deep ocean. But we'll come back to all this after spring break. All right, are there any questions on this stuff before we switch over to talking about the shallow water system a little? Yeah.
When you do this sort of comparison analysis in a paper site, how would you pick the like
XW.
XW.
So XE, you would just take whatever is as far east as you can go, just all the way to the edge of the box. But XW, you could actually think of it as a continuous variable. So what we will do, in fact, in paper 3, is do that integral where you're accumulating XE based on the wind stress, and there is a relationship between the wind stress and how fast it accumulates that we're going to find out next time, called the sphere-drip relation. And you'll be able to match it versus sea surface height and see if it agrees. And you will find that the rate of increase of height is very tightly constrained by the amount of wind that you receive along that line that you're integrating along. So it is tightly linked. And then when you go over this side, you just would fall down to whatever you fell to. And if it matched on this side and that side, then you might think, oh, well, the circulation is probably closed. If it doesn't match, then you could look for an extra current that was going northward or an extra current going southward that would have made them mismatch. Or, unfortunately, well, maybe unfortunately, interestingly, the other thing that can go wrong is that there could be a baroclinic effect, because all of this conversion between sea surface height and flow was just thinking of constant density in the upper layer. If this pycnocline came up and touched the surface, then all of that thinking gets a little more confused. Okay? Yeah?
Similarly, the depth at which you'd integrate, would that be the mixed layer?
So it's below the mixed layer. This geostrophic flow goes down, but it goes down for a while, which is kind of a fiddly part of this theory. If you did not have density variations in the ocean, it would go all the way down to a bottom boundary layer, and it would be Taylor-Proudman. So it'd be constant the whole way down. But you will see when you look at the model, or if you look at observations, which I have at the end, that that's not actually true. So this is the Gulf Stream, and you can see, so this is just velocities at different layers. And you can see it's decreasing as you go down with depth. And this, I think, is the Curacao B? No, this is just the Gulf Stream at a different location. So at this location, there's actually a deep undercurrent going the opposite direction. So it is not the case that it goes uniformly top to bottom because of the interesting things that the pycnocline is doing underneath. But in this case, you could take this depth as the depth at which, you could go down to the depth at which it reverses flow direction and just say, okay, that's my age. I'll deal with that. And that's actually not a bad approximation. So you can look at the profile in the model and decide how deep you want to go. And that should be okay.
That depth would be, could be different than the depth that you look at for Ekman transport?
It will be deeper. So the Ekman transport would maybe be 100 meters, so just that tick. This is 1,000 meters.
Okay. And that Ekman transport is at the mixed layer?
Yeah, the
Okay.
Ekman transport is pretty much in the mixed layer. Yeah. Sometimes it's a little bit shallower than the mixed layer, but it's roughly the mixed layer. Okay, let's take a quick look at the thermal wind relation, and then we'll quit. No, sorry, not the thermal wind equation. The shallow water equations. So we played the game this time of substituting gradients and sea surface height for the pressure field. And that is a nice substitution in the momentum equation. We could just do that. If we had one layer of constant density, we could just write the momentum equation like this. And because of the Taylor-Proudman theorem, we actually would know that it wouldn't tilt. It would just be one velocity, the whole thing. So we don't need to know anything except for one velocity that's uniform, and we can put back in the advection terms. It doesn't break that either. So this is kind of a nice one constant layer momentum equation. But then you might get worried about, well, how much water is there? How does this converge and diverge? And so you actually need to make up another equation that's governing the equation for the thickness variations. So if the water piles up, it'll get taller. And if it spreads out, it'll get shallower. And so basically the changes in height following the water will be governed by the divergence times the height. Okay? So this is a different way of writing the equations of motion, which is like a vertical integral of our normal equations of motion. And because we're in this Taylor-Proudman limit, the vertical integral is actually a pretty good approximation unless the density varies. So this is another way to think about it, and we could think about the gyre circulation in these equations, and it would give us the sea surface height, and it would give us the flow strength, and it would all be the same game that we just went through, except we weren't thinking of sea surface height as the moment in quite the same way. We were making a little bit of a different story for that. Does that make sense? But I don't have to stop there. I could actually stack multiple layers on top of each other, like this. And each of these has a constant density. So suppose this is like the picnic line, and that's the sea surface. And then I could think of them pushing against each other. And in this framing, the acceleration and the Coriolis force in each layer would just be given by the pressure gradient force, the same way as we always do. But this pressure gradient force would then be a hydrostatic balance summing up all of the different layers with all of their different densities. Does that make sense to everybody? This is not the way that ECHO works. ECHO solves on a fixed grid the pressure, density, salinity, temperature, UV and W velocities. There are other models very similar to ECHO that don't do that. They take layer by layer by layer, and then they sum up this way. They're similarly efficient, similarly accurate. It's just kind of a different way of thinking about the problem. Does that make sense to everybody? There's one really important case that is really useful for us, which is what if we have two layers? So this is representing the picnic line, sea surface height, and then a lower layer. And this is what you get if you sum up all of the different interface heights and the bottom depth and all that stuff. It's kind of complicated. But if you set the motion in the lower layer to 0, then the pressure is constant in that layer. The U2 is 0. And this whole set of equations really simplifies. And when you do that, you get, is that the whole system? Yeah. You get this amazing relationship, which, so it's dH1, just upper layer thickness, upper layer divergence, upper layer thickness. Momentum equation looks just like the old one, except with the upper layer thickness. So the deeper layer just goes away. You don't need to know what's happening in the deeper layer at all. You get the same system as the shallow water system, except this G prime is not the full value, it's a reduced gravity value. It just says that it's not the full acceleration of gravity, it's the acceleration of gravity times the density difference over the background density. So what that means in practice, is that if we wanted to do this case with an upper layer that was moving and a lower layer that wasn't moving, it's just as easy as the constant density case with one moving layer. So we can solve for the waves in a constant density case, and then we could solve for a wave that's trapped above the picnic line. And we would be able to compare their velocities right away. We would know that they would have a lot of similar characteristics. So this is not a great approximation to the real world, but it's a really easy one to explore. And so we'll keep coming back to this idea of a reduced gravity model with a motionless lower layer, just to kind of think about what happens if the upper layer is in motion, or what happens if a constant density ocean is in motion. And they're kind of interchangeable ideas, just because coincidentally the math of this reduced gravity system looks so much like the math of the full system with constant density. Does that make sense to everybody? I know I went through that a little quickly, but it's sort of, we can keep touching on this, but it's a little bit beyond what we need to do. And we could have done this upper layer moving, we could have done all of those integrals of, say, the stream function, because there's a sea surface height implicit in this, and we could have done that whole game. And now we know how deep to integrate. We can integrate down to the bottom of the moving layer, which is H1, from the surface down to the picnic line. So that whole story that we went through for the constant density case immediately applies to the reduced gravity case, but it helps us figure out a couple of those questions, like how deep should you go? So that depth of that surface moving layer is the one we need to think about. Okay? Other questions? So everybody, I hope, was paying attention as we were talking about the eastern boundary upwelling system, since most everybody is thinking about those, hopefully making figures with those. Yes? Things are sort of working? Ish?
Sort of.
Ish? Follow the chain slowly. Start from, what's the wind stress like in my neighborhood? What's the Ekman transport like in my neighborhood? What is it eastward? What is it northward? Is it offshore? Is it onshore? Where is it offshore? Where is it onshore? You know, like build up the story piece by piece. And then, but just the only point I wanted to make today is that that current, the California current, the Canary current, the Peru current, whatever, is not the Ekman transport. It's a geostrophic response to it. So it's fine to look at it and to talk about it in your paper and to think of it as one of the consequences of the Ekman upwelling. Just be clear on the dynamical separation. Cool. Yeah.
Should we be using the Echo dataset has the curl of the wind stress?
Yes. You probably should use that if you want to calculate, and the curl of the wind stress by tau. I calculated both of those because they're actually kind of tricky to calculate and get it right. So you can use those, and those should be proportional to the vertical Ekman velocity.
Okay.
So you can figure out what the factors are you need to multiply it by, but it's just curl of tau or curl of tau over f. And I can't remember whether I divided by rho first or not. Might be tau over rho. So it might have, you can look at the units and
So
see.
we would use that rather than just in the homework. I think one of the things is just the wind stress divided by f.
Yeah.
That wouldn't be the Ekman transport.
That's the Ekman transport, but that's not the Ekman transport divergence.
Okay.
So the Ekman transport is just tau over rho f, but the upwelling, the divergence of tau over rho f is the one that has the curl in it. And that's the one that I pre-calculated for you because it's a little tricky to get the geometry right, especially in the Arctic, which took me a while to get it all right because the grids are all going in crazy directions. Yeah?
Do you know if the sea surface height is something that, because I saw, and if no one else cares about this, I just saw that the new version has two types of sea surface height, and the Word has only one.
Yes.
And I was wondering if, speaking of that balance, the one that you have is sufficient.
The one, so in the old version of the model, there was, the coordinate system was fixed regardless of changes to the sea surface height. In the new version of the model, when they add fresh water, the surface cell actually grows a little. And so it's, there are two different flavors of sea surface height to help you diagnose those differences. Both of them should, to the level of accuracy we are thinking about, their gradient should go with geostrophy, I think, if I understand the other one right. Yeah?
In the homework, when we calculate the salinity and heat transport, there's a term called Lx and Ly.
Mm-hmm.
I wasn't quite sure.
What those should be.
Yeah.
Yeah, those were the dimensions of, like, if you were thinking of a box, you might say this was Ly, this was Lx, and then so Lx, this, let me try the right way. Lx, Ly, and Lz. So it's just the dimension, it was the dimensions of the box. So if you were considering the flow into this direction, this cross-sectional area would be Lx times Lz times the velocity would give you a meters cubed per second. Or the Ekman upwelling would be to see the cross-section of Lx times Ly.
Why is the northward or the eastward Ekman transport only multiply like Lx, not the area?
Oh yeah, it's because, well, so this is why I was saying it's a good idea to let the units guide you, because let's do tau over rho f. All right, so the units of tau are what? Meters per, or kilograms per cubic meter times velocity cubed velocity, so meters squared per second squared. And the units of rho are kilograms per meters cubed. Those cancel. And then f, 1 over seconds. So one of these cancels with that. So that has the units of meters squared per second, which is not a velocity. It is the Ekman velocity integrated from minus h to the surface. Right? So this is why I don't like the capital V and the capital U, which everybody loves to use because they just like don't want you to worry about the units. I want you to worry about the units. The units are the only way to keep track. But this is not the volume transport. This is not how much flow goes into this side of the box. This is how much volume is carried in per unit length perpendicular to this flow. You would need to integrate again, d, so V is north-south, say. You'd need to integrate in the east-west direction from x-west to x-east, which would give you this, so whatever that is, which equals tau over rho f times L x. Does that make sense? So this is why I like to write down like this. I know it's really ugly to have all these integrals, but it helps you keep track with how many meters you got, how many seconds you got, how many length scales you got. So you wanted to like regenerate those. And so that was what I was trying to do in the homework, was to make these formulas really explicit, so you at least have that one to hold on to. Because the way that Wunsch does it, he just calls this whole, he calls part of this, not this. He calls this VE, and then he doesn't even tell you what, he calls this VE. He doesn't tell you what units it got, it doesn't tell you how deep it goes, so whatever, okay? And so there are lots of different conventions of how to do that. It doesn't matter what your convention is, it just matters that you are clear about what you mean by what. Cool? All right, people are gathering for something else. Boop, boop, boop.